Okay, I think we can start today's webinar. So welcome everyone. Thank you very much for attending the 12th Fenix webinar. Today I'm Nicoleta Chiapidou from BSc. I'm the Dissemination Officer of the ICEI project. And today's webinar is about the EBRAINS services deployed on the ICEI services NMC front end, and is presented by our speaker Andrew Davison from CNRS. So thanks very much, Andrew, for being our speaker today. Before we begin with Andrew's presentation, I just wanted to let you know that the webinar is being recorded. Just like the rest of our webinars, we will upload the full recording on the Fenix website soon after the webinar is finished. And we will also upload the full presentation slides so you can have a look afterwards. The structure of the webinar is the following. So after this very brief introduction, I give the floor to Andrew to go ahead with his presentation, which will last for about half an hour. And then we will have a Q&A slot where you will be able to ask any questions or make any comments using the chat of Zoom, or you can speak out loud. You can ask to be unmuted, and I will unmute you. And also feel free to ask any questions during Andrew's presentation in the chat. I will take a note of those and I will read them out loud after Andrew has finished with his presentation. And then we will conclude the webinar with a couple of slides from my side. Okay, that's it from me. And Andrea, I give the floor to you. I will stop sharing my screen now.
Thank you very much. So I want to present this one.
Okay, perfect.
Great. Yeah, so thank you very much for inviting me to give this webinar. So I think in contrast to many of the previous webinars in this series, which have talked more directly about the Fenix infrastructure and the ICE services, this webinar is about one specific EBRAINS service deployed on top of this infrastructure, and that's the front end to the neuromorphic computing services in EBRAINS. So what I'll do in this talk, so this talk is aimed at a broad group of people, at scientists, so people who might want to use the neuromorphic systems for their own research. It's also aimed at other EBRAINS developers or people outside EBRAINS who want to use the Fenix infrastructure, and hopefully it will also, for people who might be interested to deploy their own services on the Fenix research infrastructure, this will give you some ideas or pointers of just the things we've done, and hopefully that's useful. Yeah, so I'll introduce what are the neuromorphic systems in EBRAINS, the Spinnaker and the Brainscale systems, how to use these, how you can get access to them, and then specifically how we are offering these services on top of the ICE infrastructure. So to find out more about neuromorphic computing in EBRAINS in general, you can go to ebrains.eu and then click on services, and you will find the neuromorphic computing under the brain-inspired technologies section. EBRAINS is open to anyone with an academic account, or anyone with a good reason to use it. So if you have an academic email address, you can easily create an account. If you don't have an academic email address, you can nevertheless contact us and ask for one. And you can find from this page on ebrains.eu all the documentation and background information that you might need to access these two systems, Spinnaker and Brainscales. So Spinnaker represents one approach to neuromorphic computing, so to new approaches to computing which are inspired by the brain. So in contrast to the traditional von Neumann architecture, where you have a clear separation between the processor over here and the memory over here and the bus which passes information between them, In the brain, information processing and memory is all combined into the synapses and the neurons. And so these neuromorphic systems are attempting to mimic this organization and thereby get some of the benefits which come from the brain, such as low power consumption and robustness to defects. So one approach to this is to use custom designed digital chips, which are optimized for brain models, so spiking neural network models. So Spinnaker is one such digital chip. So it's based on the ARM architecture. So you have ARM chips in your mobile phone, without doubt. And the Spinnaker is based on this architecture, and so each Spinnaker chip has 18 cores. To save space, it uses only integer arithmetic, and it has a fairly low clock speed, which means that it's overall fairly energy efficient. What makes it particularly specifically different is the network architecture. So each chip has its own router, and it has this specific geometry, which means it's really adapted for having very many cores and passing information between them. So each of these chips, which has 18 cores, is then mounted on a board. So on the board we have 48, I think, chips per board. So already the number of cores is mounting very high, and then these boards are mounted into racks, and these racks are put into cabinets, and so we end up with this machine in Manchester, England, which has 1 million cores, which can simulate many hundreds of millions of neurons potentially, together with an associated traditional computing server for running experiments and for connecting with the outside world. So that's the Spinnaker machine. That's one of the machines which is accessible through EBRAINS. The other system in EBRAINS is called Brainscales. So Brainscales is a very different approach in many ways. So rather than custom digital chips, these are custom designed analog chips for emulating spiking neurons. So rather than in the digital chip where we try to solve the equations for the mathematical model of an ion channel, for example, in a cell membrane, well, so an ion channel in a cell membrane is effectively a resistance and a capacitor and a driving force. And so we can physically build the same resistance and capacitor in silicon, in semiconductors, and so create a physical model of the of the cell membrane. And the advantage of this is that it can run extremely fast because it's so small. It's limited by the capacitance of the chips. And so in the Brainscale system, you can have speed ups of say 1,000 times faster than real time in this analog part of the system. So in this slide, I'm just showing briefly, this is the circuit layout drawing for 2 neurons. These then go into this very small region of the chip here. You can see that most of the chip area is dedicated to the synapse array, because of course synapses have there are many synapses per neuron in the brain. And so on the basic Brainscale chip, we have 512 analog neurons over 100,000 synapses. Communication between chips is then digital. So this is a mixed analog digital system where the neurons themselves are analog, but the signals between them, the spikes, are distributed via the digital network. So these individual chips are in fact left in place on a silicon wafer. So in contrast to traditional chip manufacturing, where this wafer would be split into individual chips and then each chip mounted separately, because of the fault tolerance which comes from neuromorphic architectures, it doesn't really matter if we have a few dud chips, a few broken chips. And so we can just keep the entire wafer, which is a great saving in terms of you don't have to throw away a lot of chips. And then the challenging part, of course, is then adding the connectivity on top of that. And that is done by a somewhat complex digital control system, which is carefully mounted to the wafer. And then these wafer systems are then packaged and put into these racks. And so we end up with this large scale Brainscale system, which sits in a server room in Heidelberg, but which, like the Spinnaker system, is accessible to anyone over the net through the eBrains platform. So how do you use these systems? These aren't traditional computers where you have all the existing programming tools like compilers and so on. To program a neuromorphic computer, you have to design a neural network. So a spiking neural network in this case, potentially with plastic synapses and the connectivity which is specific to the problem which you're trying to solve. And so one thing we've done in eBrains is to provide essentially a single interface which is applicable to both of these platforms. So it doesn't matter whether you're running on Brainscales or Spinnaker. In both cases, you can program them using a Python script. You build your network and specify its parameters and specify its plasticity models using a Python script, using what's called the Pine API, Python Neural Networks. And some of the nice things about Pine is that you have a single script and it will run with ideally no modifications. In practice, for the neuromorphic systems, because they're so specialized, some modifications are needed, but in general, very few modifications are needed to run the same script on traditional software simulators like Nest or Neuron or Brian, or on neuromorphic systems like Brainscales and Spinnaker. It then produces its output data in a standard format using the Neo library, which can then be read in and analyzed by other eBrains components, such as the Elephant library. And you can find more about Pine again at ebrains.eu under this the Pine service. This is what Pine looks like as a Python script. So here, for example, we've specified our cell type. We're creating two populations, one population with this cell type, another population with another cell type. We can record from all of these neurons, record the spikes they produce, we can record their membrane potential, and we can connect them together with some synaptic connection rule, and then run the simulations. And essentially the only change that's needed in principle to run this on different simulators or different neuromorphic hardware systems is to change the first line. So either you import pine.nest or you import pine.spinnaker or whichever other backend you want to run it on. And then the same code works on these different platforms in, you hope, the same way. So this is how you can, that's Spinnaker, that's Brainscales, and this is how you could, that's how you program them. Now, how do you actually send this Python program to these systems, which, as I say, one lives in Manchester, UK, and one lives in Heidelberg, in Germany. In fact, we have multiple different options depending on which stage of your project is at. For example, if you're still doing a kind of exploratory, if you're still exploring the properties of your network, you will change things frequently, change things iteratively, then you might want to access it in interactive mode. Once you're more in production mode, that your network is behaving as it should, and you want to explore parameter ranges, for example, then you might want to use the batch mode, where you can send a whole bunch of scripts off at once and explore different regions of the parameter space of your model. And in batch mode, we have multiple different access methods, depending whether you want to use the web client or the Python client, or so on. So first of all, for the web client, we have this so-called Job Manager app, and this lets you write this is available on the web at this URL at jobmanager.hvpneuromorphic.eu, or you can find it in the collaboratory. So if you're familiar with the eBrains collaboratory, you can create a new page and select community apps, and then you will find the Job Manager as one of the community apps you can install into any collab page in the collaboratory. But whether it's a standalone app or embedded in your collab, in both cases, you can provide your code in several different ways. There is an editor built in to the app, so you can directly add Python code. If instead you prefer to develop offline and you keep your code under version control using Git, then you can specify a Git repository from which the code will be loaded and run on neuromorphic systems. If you use the eBrains drive, you can select where in the eBrains drive you wish to find your code can be found. then finally, this is coming soon, or rather we had an old version of this, which we haven't yet updated with the new collaboratory, but we have a graphical model builder, which lets you kind of drag and drop populations of neurons and connect them together, and then run your scripts entirely from this graphical model builder. So as well as the code, you have to specify which platform, whether it's Spinnaker or Brainscales, or Brainscales 2 is now available. If you have a specific command line arguments that you want to have, you can specify those. If there are specific hardware options you want to use for either Spinnaker or Brainscales, then you can specify those also in this form, and you can tag your jobs so you can search and sort and find them later on. And then you submit your job. It gets sent up to the queue server, and then gets picked up by Spinnaker or Brainscales. The simulation is run, and the results get sent back to your client, to your web app. You can see here the list of jobs. So after you submitted your job, you will see it in this state here with the yellow color for a submitted job. And you can see who submitted it, when, and the kind of preview of part of your code. Once it's been queued to run, you'll see the status change to queued. And then if it finishes successfully, you'll see the green button. And if it's some error of some kind, then you will get the red button for the error. If you then, I'll come back to that slide actually. If you then click on the, here, if you click on the magnifying glass, then you see the detail of your job. So again, you can see when it was submitted and by who. You get all the output files are displayed here. So if, for example, there are figures or images which are produced by your simulations, they will be displayed in the web browser in this section. You can see the code that you uploaded. In this case, it was a Git repository, which we used. If you expand these dividers, then you'll see details of exactly which command, exactly which hardware configuration, and so on. And then you also get the full log, which comes from the machine and lets you debug or look for optimizations, in general, understand exactly how your Python script has been processed on Spinnaker or on Brainscales. Coming back to this page, so essentially to ensure that these machines get fairly used and don't get no one person can monopolize access to the machines, you have to request access to them. And so built into the job manager, you can make a request for resources. And this is fairly lightweight, unless you're requesting a huge amount. So you give a title and a summary. Only if you're requesting a very large amount of resource do you have to give a more detailed description of the project. And then this is all handled within the same app. So you submit your request, it will be reviewed. And then if it's approved, you will find that out, and you can see how much of your quota you've used up from within the app. If you want to script access, so rather than use the graphical point and click interface, you can also use Python to interact with the job queue. So in this case, this is running in a Jupyter notebook in the EBRAINS collaboratory. And here we've specified our script in a text file, which we saved to our local disk, and then we create a client which is going to access the job queue, and we run submit job. This is a bit small, I'm sorry. So this is the job. We're submitting this local script to Brainscales using a specific hardware configuration, which is given here, and using this command. And then this will be submitted, and then we can just check back occasionally to see when it's finished. And once it's finished, we can then download the data that was produced back to our local machine. If you want to use the Python client, whether locally on your own local machine, or let's say in the EBRAINS Jupyter lab, then you just run pip install HPP neuromorphic platform to install that. We also have a command line client, which is provided, it comes up bundled with the Python client. And again, this is nice because it lets you develop your code locally on your machine. and then submit your job on the command line, and then your local code will be uploaded to our central services to a temporary location. The code run on the Brainscale's or Spinnaker system. Then the results will be downloaded again to your local directory. So this is almost transparent. It feels like you're working on your local machine, whereas in reality, everything is being sent up to Brainscale to Spinnaker and then downloaded back again. And so if you've previously installed the Python client, then this gives you this NMPI, neuromorphic platform interface command, which lets you run scripts on the command line. So NMPI run, and then the name of your script, for example, -p Spinnaker. Something which is coming up which is in development is Unicore interface, specifically for Brainscales. So Unicore, for those who don't know, is a unified interface to job queue systems for HPC. So it lets you, for example, run jobs on Pitstein at CSTS or on the computers at the COR or at UNIC, using the same interface, using the same Unicore interface. And the Brainscales team is in the process of adding support for this to their system, so you can submit a job to Brainscales in the same way you would submit any other neuromorphic, any other computing job to an HPC system. And then turning now from batch mode access to interactive access. There are Jupyter notebooks running live in Manchester, which give an interactive access to the Spinnaker machine. So instead of, as was with the batch mode, you send your entire script at once. So this is like creating the network, parameterizing it, saying what you want to record, connecting populations together to make a network, and then running simulations of that network. With the interactive mode, you can create one population, do some experiments with it, add another population, add some connections, run again, and generally work much more interactively with the Spinnaker system, which in the early stages of a project, of course, has great benefits because you don't have to wait for the entire job to run before you get feedback from the system. So that's available at this URL here. I think the slides will be made available on the Fenix RI website after the webinar, so you can get all of these links then. We also have in development, in quite advanced development, a similar system for the Brainscale system, where this is going to run actually on the EBRAINS Jupyter notebooks, and will, again, interactively connect directly to the Brainscale system and let you use that in a much more interactive way. So that's the end of the part of the presentation, which tells you what neuromorphic computing is in eBrains and how you access it. This is now the part where I explain how we've used the Fenix research infrastructure to implement all of these. And here I'm talking specifically about the job queue system, so the batch mode of operation. So it's essentially rather straightforward. You have the user submits their job, as I said, to a queue server. The neuromorphic systems, so Spinnaker and Brainscales, regularly pull every few seconds. They check, are there any new jobs on the queue server? When they find a new job, it gets pulled to Manchester or to Heidelberg. It runs the job. When it's finished, it sends its output data to data storage, and it pushes the results, including links to this data storage, back to the queue server, and then the user can retrieve these results on their laptop. Because you've got the URL for the results, you can also then pull the output data from the data storage to your local laptop. That's the overview of the architecture in more detail, and this still isn't the full picture. You can kind of see how this works. So we have the queue server provides both a REST API on top of which is the web app. So that's what I showed at the start. The Job Manager app talks to this web client, which is then passing through the REST API. If you use the Python client, or if you're running Python client either on your local laptop or inside a Jupyter notebook in the collaboratory, that is talking directly to the REST API. the REST API is also talking to the EBRAINS authentication service to make sure that you have the necessary permissions to access these systems. And then all the results are saved into our job database, which is of course backed up. And then the Brainscales and Spinnaker systems are also talking to the REST API, to a different part of the API, to pull the jobs and to push the results back up. And it's worth perhaps, and so yes, and so in the context of the Fenix RI, so everything you see in blue here is services which we are running on Fenix. Then of course, in addition, the collaboratory authentication service, those are also running on the Fenix research infrastructure. In terms of how we deploy these, so this is now a developer's laptop. And once we have made some changes to the service, to the code, to the website, whatever, then we check those into Git and push it up to the EBRAINS GitLab server. Is working correctly. If the tests pass, then we push the Docker image that we've built, which contains the server image, to the EBRAINS Docker registry, running software called Harbor. And then from there, we pull the Docker images to our local virtual machines running on the OpenStack services at CSDS or in Unicore. And again, it's worth pointing out in the context of this presentation that the GitLab and the Docker registry are also running on the Fenix RI. And so in more detail, how we're using this in practice. If you want more details about this, then I recommend that you go back and watch some of the earlier webinars in this series. So webinars from Alex Upton and his colleagues, which go into much more detail about this. But essentially, we're running both our production and our staging service for the job queue, for the database backup, and for certain ancillary services on the Fenix VM services at CSDS. So our primary data center is CSDS, using the so-called Pollux and Castor systems. Pollux is the old system. We're currently migrating things to Castor, which is the new system. We also have some backup servers which are running at Unicore in the use of cloud system. And this is largely because CSDS has maintenance a few times a year when the systems are not available for a certain amount of time. And so the idea is that we can, on those days, we can run, we can switch, we manually switch the services over to running in the Unicore system. So these resources were granted to the neuromorphic platform through the ICEI project. So we made a resource request for the resources we need to run these servers, and that was granted. And so then, for the time being, we are configuring these VMs in a fairly manual way. So we're using the OpenStack dashboard. So this is in a web client. You can launch VMs, configure them, specify which size or flavor of VM, like how much RAM, how many CPUs, how many cores you need, which image you want to use, the security control. All of this can be done via this web interface, and then we SSH into the VMs which are created, and we finish the configuration directly on the VMs. So there are much more sophisticated ways to use OpenStack. For the time being, we're using it in a fairly simple way, but it's nevertheless fairly straightforward to get up and running and to add servers and remove servers whenever you need to. So in terms of our future plans, things which are currently ongoing or we plan to do in the near future. As I said, there are more sophisticated ways to use OpenStack, and so we are currently trying to increase the automation of this using the OpenStack API, the OpenStack command line, and then using Ansible to actually run the install scripts on the VMs and get them into the configuration we need to run our Docker images. Similarly, this failover between Castor and Yusuf for when there is maintenance happening at CSDS. We'd like this to be automated so that to increase the reliability and the uptime. This I think will go hand in hand with similar process being carried through by the EBRAINS technology coordination team for the other services of EBRAINS, such as the authentication. And then again, as part of the HBP work package 6, we're working on centralized logging and monitoring of all these systems. So you can, if you have further questions, of course I can answer them right now. If you think of something else after the webinar, please feel free to contact me by email or by Twitter. But please don't think that I'm the only person responsible for this. So I'd very much like to thank Domenico Guarino, Onur Artes, Jonathan Duperrier, Hassan Agrilli, Mathieu Senoville in my group at CNRS. And then in addition, I'd like to thank in particular Eric Müller in Heidelberg, who's responsible for the Brainscales end of this. So in terms of how Brainscales talks to the central queue server, that work has been led by Eric Müller. And then the same role in Manchester is performed by Andrew Rowley, who's responsible for connecting Spinnaker to our central job queue services. And finally, I'd like to also thank Björn Kindler, who has a very important role in testing our stuff and making sure it works and complaining when it doesn't. So thank you very much, Björn, for that very important role. That's all I have to say. Thank you very much.
Great. Thank you, Andrew, for this presentation. Very well structured and to the point. So we're all glad to see how you've been using the ICEI services. I think you maybe can keep your slides on if you like, and let's see if there are any questions from the audience. As I said, we can have this time now for any comments or questions. People can use the chat if they want to ask something, or they can click on raise hand. There is this option at the bottom of the Zoom window and I can unmute. Okay, we have some question. So yes, feel free to ask your question.
Yeah. Hello, do you hear me?
Yes.
Okay. Hi, Andrew, and thank you for your presentation. I have two questions. The first one is related to the HPC machines you presented, like Spinnaker and Brainscale. I'm wondering how the load balance is managed. Does the geometry, the meshes, the cells are discretized automatically by Pine or something like or something else? And is it possible to get an advanced load balance for the user?
So that is handled at a much lower level, but either by the Brainscale system or by the Spinnaker system. So I'm afraid as you saw, for example, the Spinnaker system has these 10 racks, a total of 1 million cores, but the vast majority of jobs that people want to run, networks that people want to run, do not take up the full machine. And so yes, the machine does get partitioned into different subparts, so you can run multiple smaller networks on the big machine. And then within, for each individual job, then there is a mapping algorithm which takes care of mapping the biological network, if you like, onto the physical fabric of the machine. And there's an analogous process for the Brainscale system, but I can't answer questions about the details of that. You would have to talk to the Heidelberg or the Manchester teams for that.
Okay, that's what I thought. Okay, and another question is more like a popularity one. You said that the container management is generally used for the Docker container management, the Docker tool. On the other hand, there is another tool that you know, Singularity, that is very used, highly used by machines and other teams, especially for the CSS pisdent. There is no access to the Docker to the Docker containers, but as there are many methods to as Singularity provides many methods to convert Docker's containers to the Singularity ones. I'm wondering if there is a future work or something like that in order to integrate Singularity options.
So Singularity is a very good technology, or Saris, which is a similar technology developed at CSCS. So these are great if you want to use containerization on HPC systems, where you absolutely, of course, cannot run as root as a super user. You can only have user permissions. Our use case is that we are running web services effectively, essentially on single virtual machines where we have administrator access. And so there we don't get any of the benefits of the extra features of Singularity and Saris, which are really focused on HPC solutions. Yeah. So it makes more sense to kind of stick with, yeah, I mean, Docker is a very widely used technology.
Yeah, it's very popular one.
There are advantages such as having layers. So if you change only one small part of the build process, you can it very rapidly rebuilds. You know, it caches the previously built stages, so you only have to rebuild the part which you changed. So there are quite a number of advantages of Docker specifically in this setting. So I think we have no plans to use. So I absolutely use Singularity or Saris if I was running things on pisdent, for example. But on VMs, I think it makes sense just to use Docker directly.
Yeah, of course. Okay, I understand. Thank you.
Okay, thank you very much for your questions. And we've got another one that just came in the chat, Andrew. So I'm going to read this out loud. And it says, I'm wondering whether it is possible to reach these two neuromorphic computing infrastructures from neurorobotics platforms. For instance, can I create a simulation where a brain model runs on Spinnaker and can interact with the physics engine in the neurorobotics platform?
So I think for a definitive answer to that, you'd have to ask someone from the neurorobotics platform. I do know that there have been proof of concepts of this in the past. So where neurorobotics, where let's say neuromorphic brains have been running in neurorobotics generated environments, and there is certainly work ongoing to add this kind of connection as a more general purpose, generally usable tool in EBRAINS. I don't know what the current status of that work is.
Okay, thank you. Thank you. The attendees, I will share some slides afterwards, but everyone will receive also an email after this webinar with some contact details as well. So whoever has any more questions or doubts, they can contact us and we will direct them to the right person to ask their questions as well. So we have a bit more time for another question if there is, if there are any more doubts, if someone wants to ask something using the chat or talking out loud. Let's allow a couple of more minutes. During Andrew's presentation, I also shared some links in the chat, and in this email that I mentioned, you will also receive a few more links with information about the access to the Fenix resources, the calls for proposals, and also some activities we do for our users. Okay. I don't see any more questions coming for the moment, so maybe I can start sharing my slides again just to conclude the webinar. Okay, so before we finish, I would like to share some interesting information for our attendees. So Andrew mentioned about the access to the Fenix services. So there are a few different ways to obtain access. First of all, for neuroscientists, there is the ongoing HPP brain call. There's no deadline for this. You will receive the links, as I said, in the email after the webinar. And we also have the PRAISE ICEI calls for proposals. These are quarterly, and there is the 7th call running at the moment. The deadline to apply for this one is the 29th of October. Again, all the information are available on the Fenix website, and the links that you will receive in the email after the webinar. And here you can see the page on our website where you can find all the information. It's under access. Just a very short comment to mention the survey that we would love you to complete. It's a post-training survey. We would like to have your feedback to improve these webinars, or get in touch with you if you need more information about Fenix. So it will only take you a couple of minutes. And finally, we have the Fenix User Forum. It's a platform we have for our users to interact and ask us any questions. You can find the link here, and you will also receive it through the email. You can register for free and just join the discussion. You can send us an email for any questions you have, or you can email Andrew directly if you want to ask him any questions about today's webinar. And here you also have our website link and our social media links, Twitter and LinkedIn, and we would love to see you on there as well. And so that's it from my side. Once again, I would like to thank very much Andrew for his presentation today and for answering the questions from our attendees, and of course everyone else that joined us today. And just stay tuned, as we will upload the full slides and recording on the Fenix webinar very soon.
Thank you very much.
Thank you.